Hi guys, in these days of online learning, this channel does not want you to miss anything. So if you are pursuing electronics, electrical communication engineering, this is your channel that keeps you covered. Enjoy our online video presentations in most of your modules. Enjoy. Welcome to our 60 video on electronics 1, and in this presentation we are going to look at bridge rectifier. In the last video presentation we looked at half-wave rectifier and center tape full-wave rectifier. Bridge rectifier is a full-wave rectifier, which means it makes use of both the half positive input and half negative input of our AC signal, and it is the mostly commonly used of the full-wave rectifiers. Motion Marufu is my name, and motionmarufu60@gmail.com is my email address. +26371753586 is my number on WhatsApp. Let's enjoy. Of all the rectifiers, this is the mostly used one, so it is important that you give it the attention that it deserves. Let's look at our objectives. You must be able to describe with the aid of circuit diagrams the operation of a full-wave bridge rectifier. This you must be able to do, and I emphasize it because I know examiners, because it is the mostly used one, they like it. Then you must be able to compare and contrast full-wave bridge rectifier and also center tape full-wave rectifier. Then you must be able to explain the function of filters in rectifier circuits, because normally the output of a rectifier is pulsating. So to remove those pulsations or ripples, we use filters. Then the last but not the least objective, you must be able to explain with the aid of well-labeled diagrams the operation of capacitive input filter, choke input filter, LC filters, and pi filters. The full-wave bridge rectifier does not make use of the center tape transformer. It contains 4 diodes, and according to our circuit diagram, they are numbered D1, D2, D3, and D4, and they are connected as a bridge, as you can see. D1, D2, D3, and D4. And we've got a load resistor that is connected between these 2 terminals. And let me rush on to say that this is our positive output, this is our negative output, and this is our input signal, 0 to pi and from pi to 2 pi. AC supply is fed into the bridge through these 2 terminals, or through the diagonal or the opposite ends of the bridge. These are the opposite ends of the bridge. And we've got 2 diodes that conduct at a time. And for example, these 2 diodes, they are on, which means they are conducting, while these 2 are off. And at the other input half cycle, these 2 diodes will be on and these 2 will be off. So what are we saying? We are saying if our input is positive, it is this diode and this diode that are forward biased, hence they become on, and our current is going to flow in this direction through D2, through the load, and 3 through D3, and then back to the secondary of the input transformer. When the input becomes negative, it will be these 2 diodes that will turn on. This will be off, which means our polarity will have changed. This will be positive and this will be negative. And this, if this is positive, it means this diode is going to turn on. This is the way how the current is going to flow in this direction, in this direction, in this direction, in this direction, and back to the secondary of the transformer. So please take note that this is the polarity across the load resistor, and this is positive and this is negative, and current flows through the load resistor in the same direction, hence it is DC voltage. More on the operation of a full-wave bridge rectifier. We are saying when the input is positive, current flows through D2, then from D2 it proceeds to the load resistor and then to D3 before it returns to the secondary of the transformer. And in this case, D1 and D4 are reverse biased, hence they will be off. We are now going to look at the peak output voltage. How do you find the peak output voltage? And this is AC voltage. We say the peak across the secondary because it goes through the first through D2 first. We subtract forward voltage or cut-in voltage, which is 0.7, assuming it is made of silicon. Then we also subtract the drop across D3, assuming it is the silicon. So in other words, we say peak output voltage is equal to, please take note, this is AC voltage. We say peak voltage across the secondary, if you add these two, they give you 1.4. So this is your peak output voltage. Please take note that D2 and D3 are in series, hence their addition, while D1 and D4 are in series during the negative half cycle. And as I said, the direction of current through the load resistor is the same during both positive and negative half cycles. Hence we say when the direction is not changing, it is DC voltage. In this slide, we are assuming an ideal diode, and you know that VD or VF of cut-in voltage is equal to 0. In other words, we have replaced it by a closed switch, which is the same as a wire. So we are saying when for this positive input, VM stands for maximum voltage, which is the peak voltage as well. So we are saying for a positive half cycle, our current is going to go this way, through the load and through the diode and back to the transformer, and we are going to have this voltage across the load, which is across the resistor R, and this is our output voltage. For this negative half cycle input, this negative half cycle is going to forward bias this diode. So it is going to go this way through the load resistor RL, through the other diode, that back to the secondary of the transformer. In other words, these two diodes are off when the input is positive, and these two diodes are off when the input is negative. So two diodes operate at a time. That is a summary of what happens for positive half cycle input and also for negative half cycle input. In other words, a positive half cycle input gives us a positive output across the load, and a negative half cycle input also gives us a positive half cycle input at the load. Please take note that VDC stands for average voltage, and how do you calculate it? It's 0.636 times peak or times maximum voltage, which is VM. You must also be able to convert from maximum or peak value to RMS value, and also the opposite. Everything has got advantages and disadvantages, so we are now going to look at advantages and disadvantages of full-wave bridge rectifier, and we'll start with advantages. It requires a small transformer, and it eliminates the need for a center tape transformer. Mind you, a center tape transformer has got some disadvantages. Then you realize that it's actually the input transformer is not a must, as you can feed straight into the bridge rectifier from the AC mains, especially in switched mode power supply, which will be covered in electronics too. Then the output is twice that of center tape for the same secondary voltage, because in center tape transformer, half secondary voltage is fed to the output resistor RL. Then peak inverse voltage is VM, whereas in center tape it is 2 VM, hence it is half that of the center tape. Then it has got high efficiency since it makes use of both half cycle inputs, and the average output is high. Then there's no cross saturation. Then only two disadvantages, and the first one is it requires 4 diodes. It is the only rectifier that needs 4 diodes. A center tape makes use of 2, a half wave uses 1. Then the voltage drop across the two diodes reduces the output voltage by 1.4 volts. Please take note of that slide. This is very, very important. It will enable you to draw the circuit diagram of a bridge rectifier without any hassles. In other words, you want to memorize a full wave bridge rectifier. Remember the following points. Make sure that all diodes point to the right. If you realize or if you remember our full wave bridge rectifier, all our diodes were pointing to the right. And the point number 2, both AC inputs are at the point where anode and cathode meet. You remember the anode and cathode of a diode. Where they are joined together, that's where your AC is fed into the bridge rectifier at the diagonal points. Then how do you calculate your positive output? Since this is DC voltage, this is where the two cathodes meet, or where the negative terminals of the two diodes meet. And how do you identify the negative output of the full wave bridge rectifier? This is where anodes meet. If you remember, our resistor R is connected between the positive and the anode, or between the where two cathodes meet and where two anodes meet. Take note of that, you'll need it. We have finished looking at full wave bridge rectifier when we ended with advantages and disadvantages. This time now we are now going to look at filter circuits. We've got 4 types of filters that we are going to look at: capacitor filter, inductor or choke filter, then LC filter, then pi filter. What generally is a filter? This is a circuit which removes AC components or ripples at the output of the rectifier circuit, but it only allows DC component to reach the load. So we are simply saying the output of a rectifier we have seen is a pulsating DC, and we said those pulsations are ripples, they are AC components, so they are not needed by the load. We want to eliminate them. So how do we eliminate them? We use a filter. So the simple function of the filter is to remove the AC component of the rectifier output, or the ripples, or the pulsations. So where is it installed? It is installed at the output of the rectifier and before the load. It comes in between. I've said the filter circuit is connected at the output of the rectifier just before the load. Hence, this is our filter circuit, and it removes the AC component. This is the output of the rectifier. As you can see, these are pulsations. We've got some ripples. We want a constant DC output. So the output of the filter is fed to the load, and this is a constant DC output. Normally, it is not like this, but this is the ideal. This is what we want, but you'll discover that it is this output normally is got from the regulator. Regulator is the one that gives us a constant DC output. We've only shown here for an ideal situation. So we are saying pure DC output. Filter circuits types, or filter types. We've got 4 types of filters that we are going to look at: capacitor filter, choke or inductor filter, LC, which is inductor, capacitor filter, then pi filter. Please take note that the symbol of a capacitor is capital letter C. Hence, when we are referring to a capacitor, we put capital letter C. The symbol of a choke or inductor is capital letter L. So where you see L, we'll be referring to a choke filter or inductor filter. Please take note that my last point, a choke is an inductor, or an inductor is a choke. The two words are used interchangeably. The first filter type, capacitor filter circuit. This is the capacitor that we are referring to, and this is our load. Obviously, the input is the rectifier output, which is pulsating as shown. From there to there is what we call the peak value or the maximum value. And what is happening? We are saying this is the input to the rectifier. This is the input to the capacitor. So we are saying a capacitor stores charge. So this input, which is rising, is going to charge the capacitor. And after getting to its peak value, it is going to discharge the capacitor. But what is going to happen is after charging the capacitor, the rate at which the capacitor is going to discharge is going to be very slow when compared to the decreasing value of the pulsating DC voltage. So this capacitor, the discharging of the capacitor is indicated by this red line, while the pulsations are represented by the dotted lines. So when this voltage is decreasing, the capacitor starts discharging, but it won't have time to discharge to zero as what has happened to the pulsating DC, because at this level it is going to start being charged again by the rising pulsating DC. When it gets to its peak, the pulsating DC is going to start decreasing to zero, and the capacitor is going to start decreasing also. But before it reaches zero, it is going to be charged again by the rising pulsating DC voltage, and this is going to continue like this. And this is the voltage that appears across the load. And we say we have reduced the ripples. Why? Because they are not getting to zero. Please take note that this is the way how the capacitor filter operates. It has reduced the ripples. It has reduced the AC component. How does this happen? Please take note that this is covered in your electrical engineering technology or your circuit theory course, that the opposition of a capacitor to alternating voltage or current is given by 1 over 2 pi Fc, which means if we increase F, it means that this is going to reduce, or the opposition is going to reduce. So what are we saying? We are saying some AC components, they will not get to the load. Why? Because they will be shunted to ground. They will go to ground. They will not go to the load. Hence, we are saying we have filtered out high-frequency AC components because they will not get to the load. Please take note of this. Operation of capacitor filter. I think I've gone through that, but however, let me try to hammer the following points. That the capacitor is placed across the rectifier output and also in parallel with the load RL. Then we are saying the pulsating DC is the output of the rectifier and it is applied across the capacitor. And we are seeing that as the rectifier output voltage increases, it charges the capacitor C and also supplies current to the load. Then at point A, which is at the end of the quarter cycle, the capacitor is charged to V subscript M, which is the rectifier output. But when the rectifier output starts decreasing, the capacitor also start discharging. But please take note, it discharges through the load, and the voltage across it starts decreasing as shown. And it is shown by the line AB. A is the peak, B is the voltage that it is going to decrease to. The voltage across the load will also decrease following the decrease in voltage across the capacitor, since the two are connected in parallel, but it will only decrease slightly because it will meet the next voltage peak of the incoming or of the charging pulsating DC, and the capacitor start to charge again. Because the input voltage to the capacitor is pulsating, in other words, it is rising and decreasing, rising and decreasing. It means also the voltage across the capacitor will be rising, but it will not decrease very much until it starts to be charged again by the pulsating DC. So it will follow the waveform A, B, C, D, E, F, G, and you can see that there is now less ripple. As long as the voltage across the capacitor is not going to zero, we are saying it has got less ripple. And we are also saying the output voltage is higher, as it remains almost equal to the peak value of the rectifier output voltage. Advantages and disadvantages of capacitor filter. It is easy to design the capacitors. You know, they are of small size and they cost less. Then there is an increase in the average output voltage since the voltage across the capacitor will be almost equal to the peak value. Then there is the reduction in the ripple content since the voltage is not dropping to zero as what the output of the rectifier does. Then the disadvantage is only two regulation is relatively poor as the ripple factor depends on the load. Then you must make sure that your diodes are able to handle large peak currents due to high value of the filter capacitor. You must be able to draw the circuit diagram of a capacitor filter. What we are simply doing is you must be able to connect the filter capacitor at the output of half wave and full wave rectifier. Then we are now talking about the choke or the inductor input. We are now using a wire or a coil of wire. That's what we call a choke, which is an inductor. And we are saying it is not connected in parallel as what is done to a capacitor, but it is connected in series with the rectifier output. And we know that a choke offers high opposition to the passage of AC components. Why? Because when you are talking of AC components, we are talking of frequency. And when you are talking of frequency, please take note of that formula at the bottom. It's saying XL is equal to 2 pi FL, which means as we are increasing frequency, we are also increasing the opposition of an inductor to AC components. Hence the statement, a choke offers high opposition to passage of AC, but negligible opposition to DC components. So we are saying a series inductor allows DC to pass through but blocks AC components. Take note of that equation at the bottom. XL is equal to 2 pi FL. It is very important because it shows that if we have got high ripple content or high pulsations or high AC component, it means that the inductor will block them, but it will allow DC to pass through because the frequency of DC is zero. So if you put a zero there, it means that there is no opposition to DC. It will be zero. So it will pass straight away to the load. A circuit diagram of how a choke or an inductor is connected at the output of a rectifier, and in that case it's a center tape full wave rectifier. This is our inductor L, and we are calling it a filter inductor, and our current is going to flow through the load in this direction. These are the two diodes that make up the center tape full wave rectifier, and this is the center tape transformer. And we are saying DC voltage with some problematic AC components that's pulsating DC can reach the load. And we are saying we can connect a capacitor after the inductor to filter them out. And this type of the capacitor we are going to look at in the next slide is what we call an LC filter or inductor capacitor filter. What we are simply saying is this is an inductor filter and it blocks all the AC components. They will not go to the load. Why? Because it offers opposition to the flow of AC current from the formula XL is equal to 2 pi FL. But for a practical inductor, we have got some AC components, we've got some ripples, some pulsations that will pass through this inductor. So we are saying we can add a capacitor so that it filters them out. And this is leading us to the next slide where we are going to look at LC filter. Advantages and disadvantages of an inductor filter or a choke filter. It reduces ripple in the output voltage, no surge current through the diodes is what happens to a capacitor filter. Then low ripple factor at heavy loads, which means it is able to handle heavy loads. Then the disadvantage, normally inductors are bulky, they are very big and they cost more than capacitors, and the ripple factor is poor at light loads, as we have seen that it is the ripple factor is low at heavy loads, which is an advantage. Then there is a hum sound that comes from the power supply due to the use of the choke. That is a circuit diagram of an LC filter, inductor capacitor filter. This is the inductor and this is the capacitor. And we are saying this has got a DC resistance of L, and we are calling this a bleeder resistance. But these are the critical things. This is what we call an LC filter. And this is an LC filter at the output of the full wave center tape or center tape full wave rectifier, and this is the center tape transformer, and this is our AC mains, which we want to convert to DC. So we are saying an LC filter is connected at the output of the full wave rectifier, and we are saying this is a combination of an inductor and a capacitor, and we need an inductor for low values of resistance, which is DC resistance of L, and a capacitor for high values of load resistance. What we are saying is, I think there is a phrase in one of our previous slides which talks of problematic AC components. These are going to escape the opposition of the inductor, but they are going to be dealt with by this capacitor. From XC is equals to 1 over 2 pi FC, it means that at high frequencies, this is going to be a path for AC components that have escaped from the inductor, and they are going to be shunted. In other words, this will offer, this is a ground, as you can see. So if we ground AC components using this C, it means they will not go to the load. So in other words, we would have filtered AC components using both the inductor and the capacitor. LC filter output. This is the waveform or diagram. This represents the output of the full wave center tape rectifier, and we are saying this is the output of the full wave rectifier, and this is the voltage across the load, which is also the same as the voltage across the capacitor, because the capacitor is connected in parallel with the load. So as you can see, the pulsations or the voltage changes or these AC components, we know that AC components changes in direction as well as in amplitude. So this variation in amplitude is what we call the AC components, because DC has got constant value. So we are saying the capacitor is going to charge to this value, but it will not discharge to zero as what is happening to the rectifier output, because before it reduces to zero, it is going to start to be charging again by the rising voltage of the output of the rectifier. So it is going to continue like this, but we will try by all means to reduce these ripples because they are not wanted by the load. So the bold line represents the filter output voltage, while the dotted lines are representing the output of the full wave rectifier. A look at the pi filter. A pi filter has got the shape of pi, which is this and these two capacitors. So it is made up of C, L, and C. This is the output of the rectifier. And please take note of we now have got very low ripples. So this is an improved version of all the previous filters. So what is happening is this capacitor is shunting to ground. In other words, it is preventing these high pulsations from reaching the load, so it offers less opposition. Hence, when they get to this point, they will go to ground. Therefore, they will not go to the load. This capacitor is also going to blow the AC components. They will not pass from there to there. Hence, they will go this way. Right? Those that have escaped this and this, they are going also to be shunted by this capacitor. So it will be an improved version of the output voltage, which is almost a relatively smooth output voltage. So this is CLC or pi filter. Then to remove these low ripples, we will now use a regulator. A regulator will be discussed in your electronics 2 course. Let me rush through the function of each component on the pi filter. C1, which is a filter capacitor, it offers low opposition or low reactance to AC component of the rectifier output while it offers infinite resistance to the DC component. We know that a capacitor blocks DC. Therefore, C1 bypasses, which means it shunts to ground or an appreciable or a high amount of AC component, while DC component continues its journey, while it allows the DC to go to the load because we want DC. Then the choke offers high reactance as well, or reactance is the opposition by a sinusoidal signal to the flow of AC. We are saying it offers high reactance, high opposition to AC components, but it allows DC to pass through. In other words, it offers no opposition or zero reactance to DC component. Therefore, DC is going to proceed to the load. Then the capacitor C2, which is the last component of the pi filter, those problematic AC components are bypassed to ground, or they are shunted to ground by the capacitor C2, to the effect that only DC component will proceed to the load, and this is what we desire to have, nearly constant DC at the load. A ripple factor. You must understand what is meant by the term ripple factor. Actually, we've got a formula of how we calculate ripple factor, which is the RMS value of AC component divided by the DC component. AC component is found in the output of the rectifier. Then we are going to divide that by the value of the DC component, and we are saying if we don't have AC component, it means ripple factor is going to be 0, which is what we want. We don't want any AC components at the load. So we are saying the ratio of the RMS value of AC component to the DC component in the rectifier output is known as the ripple factor. Please take note that the lower the better. So we are saying a pulsating output of a rectifier contains a DC component and also an AC component. The output of the rectifier consists of DC component, and as well as an AC component. That AC component is what we are calling ripple, and it is undesirable at the load. In other words, it must be filtered out. Then the effectiveness of a rectifier depends upon the magnitude of the AC component in the load, which means the lower the better. The smaller the AC component in the output of the filter, the more effective is the rectifier. Ripple factor is very important in that it decides the effectiveness of a rectifier, and as I said, the smaller the ripple factor, the less effective the AC component are, hence the more effective the rectifier is. Take note of that. We are now going to look at the ripple factor of half wave and full wave, and we are saying for a half wave it is 1.21, which is high, and it is clear that an AC component exceeds the DC component. Why? Because the ratio is greater than 1. This means that it results in greater pulsations or in high ripples. Therefore, a half wave rectifier is ineffective for converting AC to DC. But for full wave, it is about 0.48, which means that the ripple it is less than 1, and this shows that the DC component is more than the AC component, and this is what we want. Guys, we've come to the end of our 60th video, and it was on the bridge rectifier, which is a full wave rectifier. In the next video, we'll be looking at application of diodes. So we'll be looking at clippers. Until then, take care of yourselves. Social distancing, hand washing, vaccination are all important. Until then, enjoy yourself.